Okay, so let's do one of these multiple constraints examples. So our constraint is that we're going to be looking at a cone, and we're going to intersect it with a plane. So that's going to form some kind of a curve. We're going to call that curve C. So it's a conic section, which a conic section is by definition an intersection of a cone with a plane. And we want to find the points on the curve which are closest and furthest from the origin. All right, so that's the goal. Okay, so with this, we try and figure out what our objective function and our constraints are. So the objective function is distance to the origin, which is x squared plus y squared plus z squared, and then you take the square root. But as I pointed out before, we can find the minimizing quantity or the minimizer rather, by just ignoring the square root to make our life better. Okay, so what we're going to do is optimize or extremize the function x squared plus y squared plus z squared, subject to, and then we want, so we're going to have g1 equal, which is x squared plus y squared minus z squared, and then this is going to be fixed equal to 0. So that's going to ensure that we are on the cone. And then we're also going to require that our g2 function is x plus y minus z fixed equal to 2. And so then that will require that we are on the plane. All right. So, oh, whoops, and I forgot to label my stupid objective function. So that's f. Sorry about that. Okay, so now we go ahead and we do the Lagrange multipliers method, which is looking for solutions to this system right here. G1 equals 0, G2 equals 2. Okay. And so when we work out the partial derivatives, that gives us the new and improved system. 2x is 2 lambda 1 x plus lambda 2, and 2y is equal to 2 lambda 1 y plus lambda 2, and 2z is equal to minus 2 lambda 1 z minus lambda 2, and then we have x squared plus y squared minus z squared equals 0, and x plus y minus z equals 2. So as you no doubt spotted, this part right here is the gradient of f, and this part right here is lambda 1 times the gradient of g1, and this part right here is lambda 2 times the gradient of g2. All right, so now what can we do from these? Well, if we combine these two equations right here and solve for lambda 2, then we get lambda 2 is equal to 2x minus 2 lambda 1 x, and also equal to 2y minus 2 lambda 1 y. And so let's see. So let's collect up the lambda 1s, and we've got 2x minus 2y equals 2 lambda 1 x minus y, and I can divide the 2 from both sides and collect up, and we get 1 minus lambda 1 x minus y equals 0. All right, that gives us two possibilities. Either lambda 1 is equal to 1, or x is equal to y, or possibly both. Let's do these on a case-by-case basis. So case lambda 1 equals 1. What happens in this situation? Okay, so then if I look at the third constraint equation, which I haven't used yet, it shows me that substituting in, I get 2z equals minus 2z, and the only way that a number can be equal to its own negative is if it's 0. And so if that's equal to 0, then I can put this into one of my constraint equations, and I get x squared plus y squared equals 0, which implies that x and y are also both equal to 0. So that gives me the origin. But the origin is not on the plane, which you can see because if you were to substitute it into this equation here, you would end up with 0 is equal to 2, and that is a lie. Okay, so we can scratch that one. All right, so discard this point. And assume lambda 1 is not equal to 1. All right, then we go on to the next case. So the other possibility that we saw was that x is equal to y. What does this tell us? Okay, so then the constraint simplifies some. So let's take a look at that. So we get 2x squared equals z squared from the first one, and we get 2x minus z equals 2 from the second one. And so let's see. So if I solve this second one for z. Oh, my bad. Sorry, that was a negative 2, so that becomes a positive 2 there. Okay, now I'm going to take this and pop it in for z in this expression over here. So that gives me 2x squared is 2x plus 2 squared. And now I have some quadratic equation in x so I can solve. So I just beat on it with the algebra stick for a while. So what does that mean? That means FOIL this out. We have 4x squared plus 8x plus 4. And then x squared plus 4x plus 2 equals 0 by collecting the x squared terms and dividing by 2. And then I get from quadratic formula minus 2 plus or minus square root of 2. All right, okay, now we're getting somewhere. Okay, so now we have the constrained extrema. And there's going to be 1 at, let's see, minus 2 plus root 2 minus 2 plus root 2, and then punching in for z using the equation for the plane, I find out that the z coordinate would be minus 2 plus 2 root 2. And the other one happens when I take x and y to be equal but with the negative root. So that would be with the minus root 2 and minus 2 minus root 2 and minus 2 minus 2 root 2. Okay, so now even like one thing I could do is I could just punch these coordinates into f and see what's going on and figure out which one's the maximum and minimum. But I can actually do a little bit without even busting out my pocket calculator. So let's see. When you look at these numbers right here, each one of these, you've got a positive part and a negative part. So there's going to be some cancellation. As opposed to here, we've got a negative part and a negative part. So we're just going to get a large negative number. So each one of these is further from 0 than each one of these. That tells you that this one here is going to be bigger in the negative direction than this one right here. Okay. So if we are looking to find the minimizers of f, this one is definitely going to be a minimizer. Each one of its coordinates are smaller, so it's definitely closer to the origin. And also, the square root of 2 is smaller than 2. So since the square root of 2 is smaller than 2, I know that... oh, actually, no, sorry, never mind. I take it back. That's not what I don't care. What I wanted to notice is that... oh, well, I guess it's that reason. This right here, this is a positive number. And this right here, this is a negative number. That means that, so these two together, that tells me that the plane intersects both nappies of the cones. So the top cone and the bottom cone. That means C is a hyperbola, because that's the only conic section that has two components to it. So if you have cones like this, if the plane that you slice by has a slope, so let's look at this slope right here, the slope of the cones. Now, if you slice with something that has less slope than that, you get an ellipse. If you slice by a plane which has exactly that slope, you get a parabola. And if you slice with something that is even steeper, and only if you slice with something steeper, you get a hyperbola. Wow, that picture was a total dog's breakfast. Hold on, let me back up and just draw that like a little bit separate, because I would not be able to live with myself if I left you with that picture. Slice and slice. Okay, so there's my hyperbola. Okay, so in fact, let me drop in a picture of what's going on here. Blam! Okay, there it is. So you can see there's the cone. I have color-coded the cone by distance to the origin. So the bluer, or the more purple you are, the closer you are to the origin, and the redder you are, the further you are from the origin. And so you can see we've got this this plane here that we are intersecting with, and it intersects along this curve right here, which is a hyperbola. And so the closest point, the one that we found, is going to be, what's a good color? It's all a rainbow bright mess. Let's just go black. This one right here is going to be the closest point to the origin. There is no furthest point from the origin, because it's a hyperbola, so you can just go off in those directions forever up the curve and make the distance arbitrarily large. And this point A2 that we found, what's going on is, you know what? This is sort of a tricky one to draw. Let me draw like a real fat cone. There we go. Okay, so we are slicing it with some plane that looks like this. So we have one hyperbola here, and then we have some other hyperbola down here. And one of those points is real close to the origin, and the other is the closest point on the curve to the origin, on that connected component. But you see that this distance is bigger than this distance. So actually, this one is a local minimum, but not an absolute minimum. This one here is the local and absolute minimum, which you'll find if you punch all those points into your pocket calculator.